This is our sorts and searches, and probably going to be your last video, but I'm going to look through these review packets under this section and talk through some of the problems from there. The solutions are attached for the first one, and the solutions for the second one are posted right down here. Okay, so first of all, if we take a look at this example or this document, this was scanned from that Barron's review, and remember this is the one that also has the solutions all in and explanations. And so I'm going to be spending less time because it does have the explanations here on a lot of those. I'm just going to kind of scroll through and hit a few of the critical ones with you. Not all of them, but just to give you some hints. Okay, so on question number 9 here, this one is actually similar to what we did. To find the key value 27, the search interval after the first pass for the loop will be, and so it's just trying to get you to decide, is it on the low end or the high end? If I'm looking for 27, if it's doing a binary search, it should divide it in half. So I have 8 elements, so if I do low plus high, that is going to be 3.5. so it looks at position 3 and it determines 27 is greater than that, so I am left with the right hand side. Okay, and then some of these other ones are similar to what we already talked about, so I'm not going to go through them, like how many iterations, what will be stored in Y after executing the following binary search for, so they're wanting you to trace through it. If the test for the while loop is changed to low, less than high, what value in the given list will not be found, etc. So take a look at some of these. You don't, number 3 I don't think is one that's a high emphasis, but I would go ahead and do these and then check with the answers so you can just make sure that you are kind of on target. I am going to spend a little bit of time on number 14 here. It says a large sorted array contains 30,000 elements and is to be searched for a value and a value key using an iterative binary search algorithm. Assuming the key is in the array, which of the following is the closest to the smallest number of iterations that will be guaranteed that the key will be found? And this is one where we could use that base 2 notation. They are telling you here 2 to the 10th. Remember back on our spreadsheet here, 2 to the 10th is approximately 1,000. Okay, and so if I go back and the other thing, if I take a look at 2 to the 10th, 2 to the 10th is for 1,024 elements. So if I keep going up with my powers of 2, then I'm going to have a rough idea of how many. I'm looking for 30,000 elements, so I'm going to keep going up my list, powers of 2, and I'm going to be looking for 30,000 elements. Or you could use something like this. Keep in mind that if you have 2 to the 10th and then times 2 to the 10th, if we're calculating and we multiply with common bases, 2 to the 10th times 2 to the 10th is going to equal 2 to the 20th. And so what that's going to tell me is that I know 2 to the 10th is approximately 1,000 elements, and then if I multiply by another 1,000 elements, that's going to equal 1,000,000 elements, and that's way too high. And so I know it's got to be somewhere between 2 to the 10th and 2 to the 20th, because 2 to the 20th would be approximately 1,000,000 elements. And so by default then, all the rest of these down here are going to get canceled out, and the correct answer is 15. The correct answer is 15. So you can get your calculators out and do 2 to the 15th and see that it's going to be in the ballpark of 30,000 elements. I don't know what it actually is, but it's going to be close to 30,000. So that's how you can use that base 2 notation. Okay? The next few questions on here are, after the third pass questions, so you should practice those. I want to look at question number 17. It says, when sorted biggest to smallest with the insertion sort, which list will be need the greatest number of changes? So here's where so I wanted to go from largest to smallest. So if I start to look at the patterns here, the first array has already has like small numbers first and then large numbers on the end. The second and the third choices have some smaller numbers towards the end, and D, 2 and 0 are towards the end here. But what we're looking for, and what you guys probably don't know yet, is that the insertion sort has the most number of changes to it, or it's the worst case scenario when the digits are basically in reverse order. So this one is pretty much in reverse order because it goes 1, 2, 3, 4, 7, 6, 9, and 5 is the only one that's kind of not in order there. So because it's pretty much in reverse order from what it needs to be, the list that needs the most number of changes is going to be A on that particular one. Question number 18, you're using the compare to method. You're not going to really need that for this next test, but that's a good one to look at for AP review if you're taking the AP exam. Next few algorithms, if an array contains the following elements, what would it look like after the third pass of a selection sort? And again, you don't have to know all of this code right here, and I think that actually, I don't know if that belongs to the same question or not, but you do have to know like how many passes, etc., that kind of question. This one's a good one to look at here. Number 20, it says the element is in a long list of integers roughly sorted in decreasing order. No more than 5% of the elements are out of order, which is a valid reason for using the insertion sort rather than the selection sort on this one. And so your choices are, it will be fewer comparisons, there will be fewer changes of position, there will be less space required for the insertion sort. So it's trying to ask, why do I want to use the selection sort compared to the insertion sort? So that's question number 20. I'm just going to peek at the answer. The answer is A. I'm working backwards, and if I take a look at this, A is 1 only. So it says there will be fewer comparisons of elements for the insertion sort. And so, and again, that's not always going to happen. And most of the time it actually will. Actually, on the insertion sort, you don't do as many comparisons. But these other two won't necessarily happen when you're doing an insertion sort versus selection. The key here is that it's a long list of integers, and they are already roughly sorted in decreasing order. No more than 5% of the elements are out of order. So that helps you make that decision. Next, if we take a look at, and so you want to look at these questions like number 22 and do like what I just did, kind of work backwards, okay, and see what the solutions are. I'm just looking for a couple more that might be useful. Here's a good one to use that base 2 on. A binary search is performed on an array with 600 elements. In the worst case scenario, which are the best approximation for the number of iterations? So if we look at our base 2, and I'm looking for 600 elements, 600 elements falls between 8 and 9 on my powers, and so I'm going to say it has to be, at least 10, because 10 is closer to the, the 8 or 9 than 6 is. So that's question number 28. If we look at question 28, the correct answer is B, and we use that by using those powers of 2. The worst case scenario for the insertion sort, this one we just actually kind of talked about. It's the fact that the list is in reverse order. So when the list is in reverse order on this, that's going to be the worst case. Okay? Maybe a couple more, and then we might move to the other review sheet. This is one where it talks about putting them in low to high. So you have these 3 tasks: sequential search, binary search, insertion sort. You need to compare the big O notation, and then you need to put them in order from least to greatest for their average runtime. So look at your big O chart and you put these in order from least to greatest using that, okay? And that's it on that review. The other review sheet is very similar. It does have a little bit more refined questions. For example, after 5 iterations of the selection sort working on an array of 10 elements, what must be true? So if I've gone through 5 iterations on a selection sort, 5 more iterations are always necessary, 4 more iterations are always necessary, 5 more may be needed, 4 more may be needed. This is going back to that question of how many times do you have to iterate through a selection sort, and we talked about that back here. On a selection sort, it's always going to be one less. This said 6 iteration, but that's because there were 1, 2, 3, 4, 5, 6, 7 elements. So it's always one less than the number of iterations. So if I've already done 5 and there's 10 elements, I need 9 iterations. The answer is going to be B. But this is an excellent review to go through. It might be a couple repeats, but the solutions to those are posted right down here on course sites. Okay? So I know there's a lot of talking here. I know these aren't like the best, most refined videos, but if you actually listen to all 4 of these, you should be sitting pretty good for your test coming up.